Welcome to lecture number 7 for ECE 321, Analog Electronics. In this lecture, we're looking at filters, building active filters. A little bit of background. A filter is a circuit whose behavior changes with frequency. That's pretty much any circuit that has capacitors and/or inductors. When you have a filter, we use sine waves to analyze the circuit. That allows you to use phasor analysis. For example, take the following RC filter. Find y in terms of x. The differential equation relating x and y is the derivative of y plus 5 times y is 5 times x. With filters, we like sine waves. The reason being that sine waves are eigenfunctions. What that means is that the output is the same form as the input. That's only true for sine waves, not true of anything else, pretty much. For example, if the input to that RC filter is a square wave, the red line, the output is the blue line. And it's kind of hard describing the relationship between the two. They don't look the same. On the other hand, if the input is a sine wave, like on the bottom, then the output is a sine wave. The only difference is the change in amplitude and a delay. So likewise, I can represent the gain of the filter with a complex number. That allows us to use phasors. Phasor analysis is kind of how you analyze differential equations with sine wave inputs. It's the forced response for a differential equation with sinusoidal inputs. For example, suppose I have the following differential equation, and the input is a sine wave. What you would do back in math and calculus, you would assume the form of the answer. Y is in the form of a sine 6t plus b cosine 6t. Take the derivative, substitute, match coefficients. Kind of a long, painful way to do it. With phasors, it's much easier. With phasors, I replace the derivative with s. So derivative of y becomes s times y. Plus 5 times y is 5 times x. Solve for y in terms of x. This is the gain. It's a function of frequency, or function of s. For my input, the frequency s is J6, so analyze the filter at the frequency of the input, analyze the J6, multiply by the input. And in phasors, the real part is cosine, minus j is sine. So this is 0 cosine, 1 sine, 0 minus j1. Multiply them all together, I get a complex number. The real part means cosine, the complex part means minus sine. So with phasors, I can solve this differential equation fairly easily. I just have to use complex numbers. That's why we like phasors. That's why we love sine waves in electrical and computer engineering. Bode plot is a graph showing the gain versus frequency. So with filters, analysis is actually pretty easy. If I have a specific sine wave as an input, I just analyze that filter at the frequency of the sine wave times the input gives you the output. If I don't know the specific input, I can kind of do a generalized gain. I can sit there and calculate the gain at a whole bunch of frequencies. Here I'm picking 100 frequencies between 0 and 10 radians per second, calculating the gain at each frequency, and then plotting the magnitude of the gain. Again, g is a complex number. It's got a real part and a complex part, which doesn't mean a whole lot. And polar form has an amplitude at an angle. The amplitude is the gain. The angle is the delay, which delay doesn't really mean much to me either. We usually just plot amplitude. That tells you the gain. So this is a graph of the gain. At 6 radians per second, this is the gain that we had in the previous problem. In general, this is a low-pass filter. It passes DC signals with a gain of 1, and the gain slowly tapers off. So it's not a very good low-pass filter, but it is a low-pass filter. Low frequencies tend to get passed more than high frequencies. So that's filter analysis. Again, you just plug in S equals j omega and you have it. Filter design is a little bit harder. When you design a filter, we're going to want to actually implement them. Today we're kind of looking at various circuits that allow you to implement the filter once you design it. How you design that filter is going to come up later. So the circuits we're going to look at are kind of like the Legos, the building blocks you can use. We're going to look at an op-amp circuit that allows you to build a filter that's a low-pass filter, high-pass filter with real poles, complex poles. Op-amps allow you to build circuits that have a gain bigger than 1. They allow you to have a high input impedance, low output impedance. They also allow you to implement circuits with real poles and complex poles using only inductors and capacitors. We try to avoid inductors since they tend to be large, lossy, prone to coupling, expensive. Otherwise, they're great. So really, we prefer using capacitors and resistors, given a choice. So a generalized filter kind of looks like this. I've got a gain k, I've got a numerator polynomial, a denominator polynomial. The numerator polynomial are called zeros because at these roots, if I plot the frequency versus gain, if I have a zero at a certain frequency, the gain goes to 0, hence the name 0. If I have a pole at a certain frequency, the gain takes off to infinity because I'm dividing by 0, kind of like I have a telephone pole sticking under the omega axis right here, hence the name pole. So that's a generalized filter. Today's lecture, we're going to look at how to build a circuit to implement a filter that has real poles and complex poles. So starting out, let's look at a circuit that just has real poles. If I have real poles and a DC gain of 1, I can implement that with an RC filter. To avoid loading, I'm going to take each resistor and increase it by 10 times. And then roughly, the poles are just 1 over RC. And you can kind of do that if we just have a single RC filter. The Laplace impedance is 1 over CS. So by voltage division, it's what I'm measuring over the total. Clear the fraction. Sure. 1 over RCS plus 1, or the way I like writing it is 1 over RC S plus 1 over RC. So here's the pole. On a pole at A, this 1 over RC is A, this 1 over RC is B, this 1 over RC is C. The nice thing about RC filters is they're easy to build, easy to implement, all good, but they're not very good filters. Second version is I can do that with an op-amp. This allows you to have a gain that's bigger than 1 or less than 1. Here I've got 2 constraints, 3 degrees of freedom. I know it's a first order filter because I have 1 capacitor. The number of capacitors tells you the order of the filter pretty much. So I know the filter's in this form. If I take the limits as S goes to 0, I have a gain of A over B. S goes to 0, capacitor doesn't exist, and R1 over R2 is the gain. That's A over B. I've got a pole right here at DC. This is a resistor. At high frequencies, it's a capacitor. I switch when the two are equal to each other. So when R1 is 1 over CS, that's where I switch. Or S is 1 over RC, and where I switch is at B. At DC, this is B. High frequency is S. I switch at B, which is what happens here. These two are the same at B. So pick R1 so that 1 over R1C is my pole. Or a third way to do it, as S goes to infinity, this is a short, and I just have an integrator, or differentiator, I mean. That'd be an integrator. And the gain is 1 over RC. So 1 over R2C is as S goes to infinity. A is 1 over R2C. For example, suppose I want to implement this filter, 50 over S plus 100. I've got 2 constraints, 3 degrees of freedom, so somebody's arbitrary. Let's just for fun say that C is 1 microfarad. You can pick anyone you want and set it. I'm just going to set C. The pole is at 100, so 1 over RC is 100. This is 0.01 microfarad, or 0.01 mega ohm, or 10K. The DC gain is 1/2, so this is going to be 20K. At DC, the gain is 10K over 20K, 1/2. That's the second filter. The nice thing about this one is the gain can be bigger than 1, less than 1. The RC filter, the DC gain is always 1. The other nice thing is I can cascade a whole bunch of these. I don't have to keep on making R get 10 times bigger. the input impedance of the op-amp is infinity, ideally. Output impedance is low. I can cascade these and not have any loading issues. But it takes an op-amp to implement each stage. For example, suppose I want to implement this filter. 500 over S plus 2, S plus 5, S plus 10. To do that, I could do this a couple ways to do it. One approach is this has a DC gain of 5. I need an op-amp. I can't get a gain bigger than 1 just using an RC filter. I'm going to pick this one over RC to be 2, this one over RC to be 5, this one over RC to be 10. To avoid loading, I'll do something like, let's make this 10K, 100K, and 1 meg. 1 over RC is 2, so this becomes, let's see, 1 over RC is 2, 2 times 10,000 inverse. This becomes 50 microfarads. 1 over RC is 5, so 5 times 100K inverse. This is 2 microfarads. And let's see, 1 over RC is 10, 0.01 microfarad. That sets this guy, DC gain is 1. To make the DC gain 5, you can plug in S equals 0, you get a gain of 5. I want this to have a gain of 5, so make that 4K and 1K, DC gain is 5. In Circuit Lab, I can check that. Wrong circuit. So again, in Circuit Lab, I can implement it, build the circuit. That should be 0.1 microfarad, and error in the calculations there. To check the filter, I can go under Simulate, Run Frequency Domain Simulation. Now, when I do that, I can add expression. I want to look at the input. Well, that's just going to be 1. Look at the output. And phase, I really don't care about. The normal is dB. I personally like magnitude. Yeah, pick your favorite. I like magnitude, so it kind of shows the gain. So this will be the magnitude of Y, going from 0.01 to 100 Hertz with 20 points per decade. If I run it, here's what it looks like. So at low frequency, the gain is 5. The RC filter has a DC gain of 1 times a gain of 5 for the op-amp. And then the gain kind of slowly rolls off. Slowly rolls off like this. So that is an RC filter. I could also build it using the op-amps. Again, the trick is I want to separate it into 3 terms. How I distribute the numerator is kind of arbitrary. Typically try to keep the DC gain about the same for each stage. So if I spread them out this way, that kind of works. For each stage, I have 3 degrees of freedom, 2 constraints, so somebody's arbitrary. Let's make this a 1 meg resistor, make that a 1 meg resistor, and make this a 1 meg resistor. 1 over RC is 2, so this is 0.5 microfarads. 1 over RC is 5, so this is 0.2 microfarads. 1 over RC is 10, this is 0.1 microfarad. This has a DC gain of 2.5. So this would be 400K. 1 meg over 400K is 2.5. This has a DC gain of 2. So this is half a meg, 500K. And a DC gain of 1 meg. So this is another way to implement it. Take your pick, either one's fine. This is a little bit better, a little more accurate, but it takes 3 op-amps. So that's with real poles. Real poles are really easy to implement, but they're not very good. If I have complex poles, that's a different circuit. This is a circuit that'll do complex poles. Again, this isn't real obvious. I got this out of the back of the electronics book, or Wikipedia, that also has it. Essentially what you have is positive feedback. If I take this capacitor, tie it to ground, I have the previous solution, a two-stage RC filter, two row poles. This is one of the few circuits that you'll ever see that has positive feedback. Positive feedback is like at a rock concert. If I crank up the volume, the sound goes from the speaker through the air to the microphone to the amplifier back to the speaker. At a certain frequency, it's going to add in phase. If the gain of that frequency is too big, I get this horrible screeching. That's when you go unstable. That's what I want to do here. I want to add positive feedback to make this go unstable, to make it screech. If there is no feedback, I'm on the real axis with real poles. Add feedback, I start moving in the complex plane. These poles shift out, and eventually I go unstable. If you grind out the equations for this circuit, it winds up being this. What happens is, 1 over RC, that sets the amplitude. That's this guy right here. The angle is set by R1 over R2. This angle is 3 minus K is 2 times the cosine of the angle, and K is the gain of this one, 1 plus R2 over R1. So I can set the amplitude and set the angle. I'll wind up with the DC gain. Typically, you don't really care. What the DC gain does is it adds gain. Typically in the amplifiers, I'm going to want to amplify my signal anyway. This will give you some of the gain. The circuits we looked at before will give you the rest of the gain, like the inverting amplifier, non-inverting amplifier. So this one just kind of match the denominator and live with the numerator. And the gain that you want, R2 over R1, at this point, K is 1. At this point, K is 3. If you ever calculate K and it's bigger than 3, you did something wrong, because beyond 3, you're unstable. So K should be somewhere between 1 and 3, following these equations. And we'll go through an example in just a sec. Slight variation, if I swap R and C, that gives you the same equation as before, but now I've got 2 zeros in the numerator. What the first one did is the gain kind of does this. I've got 2 poles in the S-plane, the gain's fairly flat out to the pole, then drops off. In this circuit, the gain is 0 at DC, that's the S squared, and then at 1 over RC, the gain roughly becomes 1. So this is a low-pass filter. This guy right here, that's a low-pass filter. No zeros, 2 poles that are complex. This is a high-pass filter, 2 complex poles, and 2 zeros at S equals 0. And the third one, the last one we're going to look at, is a bandpass filter. Again, this is one that's real obvious. You could derive the equations. I've got 1 node, 2 nodes, 3 nodes. I know this node is 0 from V plus equals V minus. Solve. Sometime later, you'll get this. Yeah, don't know what that is. Ignore this term. So this will have 2 complex conjugate poles, a 0 at S equals 0, and a pole. What that does in terms of gain versus frequency, the DC gain is 0. That's from this guy. As S goes to infinity, I get 1 over S, goes to 0. And in the middle, I have a high gain. That's a bandpass filter. So for example, that's kind of the shopping list of types of filters. If you want to build a filter, start with a transfer function. Assume this is given to you. Come up with a circuit to implement it. Well, the trick is I have to sit there and look at the transfer function and figure out what circuit that corresponds to. Here, I don't know which one that is, but I can factor out a real pole and a complex conjugate pair. This is an RC filter, so that'll be this guy. This over here is complex poles, no zeros. That's this circuit. To build it, what I'm going to do is take the first term. This is your 85 over S plus 85. That term. I can pick R to avoid loading. Let's let this be 10K. Make this 10 times bigger. And for this circuit, these two are the same. For an RC filter, 1 over RC is my pole. I want 1 over RC to be 85. R is 10K, solve for C. C is 1.17 microfarads. For this one, 1 over RC is 121. And that's this guy right here, the 121. R is 100K, solve for C. C becomes 0.082 microfarads. To set the angle of the pole is 69 degrees. And pole right here, I'm at 69 degrees. Here, K is 1. Here, K is 3. I'm at 69 degrees. 3 minus K is 2 times the cosine of the angle. Find out K is 2.3. K is this gain, 1 plus the resistor ratio. I want a gain of 2.3, meaning make these 1.3 to 1. Pick something for R1, like 100K. This is 1.3 times that, 130K. So when you're all done, here's your circuit. Note that originally the DC gain is supposed to be 1. This has a DC gain of 2.3. So what I could do, probably easiest, is say that this output is 2.3 times Y and leave it alone. Presumably some other part of the circuit is going to have some gain. This circuit gives you gain of 2.3 free of charge. That just means the rest of the circuit needs less gain. So easiest to just change the label of the output, call that 2.3Y. And Circuit Lab, if I can find it. Yep, there we are. Here's the circuit. If I want to see how it behaves, this would be the analysis part. What I would do is just plug in S equals J omega, analyze it. In Circuit Lab, I can do that. I just do under Run Frequency Simulation. What I'm going to do is look at the output V2. I'm going to sweep V0, this guy, going from 0.01 to 1000 hertz with 100 points. I don't care about phase. I personally prefer magnitude. Other people prefer dB. Take your pick. And then run. So here's the gain versus frequency. The gain stays at a gain of 2.3, that's K. The 1 plus R1 over R2 stays fairly flat. I get a slight resonance right here, then the gain drops off. If I plot it between 1 and 100 hertz, I might get a little bit better picture about it. Let's go between 1 and 100 hertz. Spreads it out a little bit. So there's your gain, 2.3. This one has a slight resonance and then drops off. One last example. Come up with a circuit to implement a bandpass filter. So this one, as S goes to 0, the gain is 0. If you analyze this in MATLAB, what's going to look like is it starts out at a gain of 0. It then has a gain that's fairly flat, then drops off. This one has a corner at 10 radians per second, so at about 10 radians per second, the gain becomes flat. This has a corner at 100 radians per second. At about 100 radians per second, the gain drops. Come up with a circuit to implement that. Well, again, we don't have a circuit to implement that, but what I can do is separate this into two terms. I'll pull the S squared over here, the 10,000 over here. Now this is one circuit. This is the low-pass filter with two zeros at S equals 0. This is the low-pass filter with no zeros at S equals 0. That's going to look like this. So here's the first circuit in red, the second one's in black. To find the values, what I would do, let's start over here. I've got one constraint, 2 degrees of freedom, so either pick C or pick R. Let's pick R. Let's see what I did. I said R is 100K. Kind of arbitrary. If this is 100K, this is 100K. I want that first stage to be, let's see, factor this, that's S squared plus 7S plus 10. Oh. The first one, the pole is at 10. So pick R, solve for C. The angle of the pole is 45 degrees. I'm going to use MATLAB to factor those poles. This is 10, that plus minus 45 degrees. 3 minus k is 2 cosine of the angle, gives you k is 1.58. That's 1 plus the resistor ratio, so make that 100k and 58k. That's the first stage. The second stage, here's the generalized form. Here's the filter I want to implement. You can kind of ignore the numerator. I just want to match the denominator. The amplitude of the pole is at 100, angle's at 60. So 1 over RC is 100. Here I picked C, solve for R. The angle is 60 degrees, tells you that K is 2. Pick R1, 1 plus R1 over R2 is 2. So when you're done, here's your circuit. There's the first stage, there's the second stage. The midband gain of the circuit is actually 3.28. That's because this has a gain of 1.58. This has a gain of 2. It's supposed to be 1. Simplest way to solve that is label, change the output. Instead of calling that y, I'll call it 3.28 times y. So that's kind of circuit implementation. With active circuits, I can implement circuits with real poles, complex poles, gains bigger than 1. And you kind of have to look at the filter you're trying to implement to figure out what circuit you want to use. It's kind of like Legos. I've got different building blocks. You just cascade the different building blocks. To build a circuit, build a filter, what you do is you factor the filter into sections with real poles and complex poles for each section. If I have real poles, implement it using an RC filter or an RC active filter. If I have complex poles with no zeros, I'll use one circuit. If I have 1 0, another circuit, 2 zeros at the origin, use the third circuit. And just kind of cascade them. Again, it's kind of like building blocks, kind of like Legos. So that's lecture number. Implementing active filters.